Next thing, basically, yeah. Once every 2 weeks, I shave. About every month, I force my kids. Come on, kids, shave my head, or you're in trouble. So
Oh
that's
my
how.
gosh, you put a lot of faith in them, man. I heard shaving your head's pretty hard.
Well, yeah. It's yeah, let me put it this way: the first time I was a little bit scared, and I had to throw something across the room because I thought I was going to get cut. And there was a few times they really dug it in there, but yeah. Um, so, but yeah, I make yeah.
It's looking good though, man. It's looking
All
good.
right, I appreciate that. Yeah. Yep, it works. All right. So let's go ahead, and our goal is, again, you have a quiz Wednesday. We want to get as much practice as we can. Anytime you need to, you could work with Jay. And so let's start with the problem together, maybe do a breakout sesh, and then come back and do some more problems together. And if you're getting tired of the breakout sessions, just let me know. You could put that in the chat or whatever, but I don't want to do them all the time, but maybe one a day. We'll keep it to that. So let me start with the screen share. And we are in the workbook. This is chapter 5, number 31. Whoops, 31 is at the bottom of page. It's at the bottom of page 92. At the bottom of page 92. All right, and so this problem's going to be a little bit different, but it uses a lot of the same stuff we've been doing already. So we have a block of mass M hangs on a massless inextensible string. Unless otherwise specified, all of our strings are massless and inextensible. Remember, the inextensible part relates to making sure that the two sides, it's not stretchy, so the two sides move the same amount, so they have the same acceleration magnitude. Massless means acceleration will be constant because you're not transferring mass from one side to the other. And then lastly, if you have negligible mass and axial friction, that just means the tension is the same on each side of the string. So this means same A magnitude, this means A constant, and this means tension same on each side of string. All right, that stuff's not that important, but it is worth noting a couple of times as we get started. Those things right there all matter. All right, so mass M is right here. And then we've got a second block of mass 3M right here. And the angle theta can be adjusted by a local zombie. And then friction is negligible. Okay, so I see what we're doing here. It says, at what angle will the two blocks be in equilibrium? Now, just in case I haven't said this before, what does equilibrium mean to you? You can unmute and just say whatever you think.
It means like at rest for both things.
Okay, they would be at rest in equilibrium. It turns out that's a special kind of equilibrium. That means static equilibrium. So that's the extra word that sometimes we use. So what you're saying describes a static equilibrium. That's good. And so that's a consequence of equilibrium, but I wouldn't say that's what equilibrium is. So that was a good thought. It was correct, but it just wasn't what I was looking for. So does somebody else have an idea what equilibrium means?
Is it when their forces that they're applying like on each other are equal?
Okay, that sounds pretty good.
Balanced.
So yeah, forces can be balanced. And now you see why there could be static equilibrium or dynamic equilibrium. You could be moving with constant velocity, acceleration would be zero, and the forces would still balance. So in general, anytime the forces balance or the forces equal each other, I think that was either Dom. Was that you, Dom?
Yeah, it was me.
Yeah, so I would say this is a more general definition. The other one was a special case that happened to apply to this problem only. So both of those were excellent answers. All right, so if they're at rest together, we call that static equilibrium. Anytime it says equilibrium, that just means forces balance. All right, so another way of saying this is when you see this word, if the force is balanced, what's the acceleration?
Zero.
Zero. So that's another way you could view equilibrium. This is a key word. If you see this in a physics question on your quiz, you're supposed to know equilibrium, ding, 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 forces balance. That means A equals zero. All right. So basically we're saying at what angle will A equal zero? All right. So go ahead and take a second. The general strategy here is to draw FBDs. So draw an FBD for this block, draw an FBD for that block. And I would recommend choosing a rotated coordinate system here. So I would recommend, well, let's talk about this. Let's start with this block 3M. Which way do you want to call the positive direction? It doesn't matter, but what would you call it? Anybody that speaks up is fine. There's no wrong answers. What direction would you call the X for this one, for 3M?
Parallel to the line.
Okay, so you could call it this way or that way, right? And you could do the standard one, but it turns out that will actually make life harder, just so you know. So you could do this way for X. It just turns out in this particular problem, it ends up being a bad choice, not a invalid choice. It's just harder, slightly. So which would you rather do, up the plane or down the plane?
Up the plane.
Why not? And it doesn't matter, but as long as we pick this, and so then once I do that, probably it makes sense to do Y up the axis, Y perpendicular to the plane. And so then look at this. If I do this one, I highly recommend doing what I'm about to do here. Rotate the axes around with it. So once you define one of the blocks, let the other axis follow it around. And so this one, I would actually call the X-axis down and the Y-axis out. Not that you have to do that, but I just recommend it. Now here's why. Again, you don't have to do this. It's just what I recommend. If this thing was going to accelerate, we would think it would go this way. And then if this one was going to accelerate, we would think that one would go this way. Now, in this particular case, we were told the acceleration value is equal to 0. So that doesn't matter that much. But again, the reason for doing this, it sets you up for circular motion problems later, and it reduces possible minus sign errors once you get used to it. So that said, everybody try to draw your free body diagrams using the 2 coordinate systems I have shown. So again, let me get my eraser on this. Whoops. Use that orange coordinate system there for each block, and we don't need these ones, I guess. That was just from rotating it around. So use the given coordinate systems, draw your FBDs, write your force equations, see if you can figure out the angle. I'm going to try to get this thing started on my own whiteboard, okay? Oops. .31. Yeah, kind of caught up. Okay, so here are the free body diagrams, I think. Maybe you had a second to work. I hope so. Maybe you could check that, see if that's what you got, or ask me any questions.
So you drew the two boxes separately, right? Like
Yes. Oh, so this would be the 3M FBD right here. And this is the FBD of just M by itself. You could try to do a system FBD for this one, but I don't recommend it. It's just easier to do the two separate. So in this case, I see that this one doesn't line up with the coordinates. So I'm going to split that up. Tell me what I'm doing wrong here, everybody. Watch what I do. Tell me what I did wrong.
It's not parallel to the X-plane.
Exactly. This one doesn't match that. Oops. The other way to see that is, see how this component is longer than the vector itself? That's a sign you didn't split things up right. That looks a little bit better. And notice the right angle is always opposite the magnitude itself. All right, so in this problem, which of these two angles is theta? Is it the upper angle or the lower angle? If it helps, remember, you could always kind of draw in this triangle here.
Is it the lower angle?
Let's see. This is theta, right? So what's this angle here? Theta or 90 minus theta? If this is a right angle and this is theta, what's left for that?
90 minus theta.
So then what's left for this? Because this is a right angle too. So what's left in here?
theta.
Theta. So this is a cool trick you could do. Even though this isn't really part of a free body diagram, sometimes what I'll do is I'll actually use the MG arrow and a right triangle to help me figure out where theta goes. So in this particular problem, theta was marked down here. So I use this MG to get me a right angle, give me a 90, and that helps me see that. That's a cool trick. Also, let me just steal something from the internet really quick here. The other day, whoops, oh, come on, where's Zoom? The other day, I worked with a student in office hours, and I recorded a little video, just 4-minute video showing angle practice. So I believe I correctly linked that video there. It should be a 4-minute video on angle practice. Jay, if you want, you could confirm that that is the right link and that it works. It should work. But so that's a backup for you if you need it. If you don't remember how to do the angles, that's a good video. You could watch it after class. But for now, and Jay's going to confirm that works. But for now, let's assume we did this practice right. So that's my trick. Draw the angle, use MG to get a right angle, figure out the thetas and 90 minus thetas. All right, thanks, Jay. So that should work for you guys after class. All right. All right. Other questions on this? Cool. You could have just called this a letter N, because in this problem, there's only one normal force. So there's no need for a subscript. So some of you probably didn't even put one. And I agree. I probably wouldn't put one normally. So you could either call it N subscript 3, or you could call it just N, since there's only one normal force. Who cares? So in this case, I probably will just do that. All right. So go ahead and write the forces in the X and Y direction. This one, notice only the X direction matters. Actually, let's do it together just to have a little more fun. How about for 3M? Give me the free body. Give me the force equation in the X direction for 3M. Give me one force in the X direction on 3M.
T.
T, positive or negative?
Positive.
Yep. Okay.
Minus 3 mg sine theta.
And in this case, what's it all equal to?
MA.
Nope.
All right. Acceleration 0, so it just equals 0.
True. But what is wrong with saying MA? So this, you could always plug in that A equals 0, but this is still wrong. What did you forget?
3 MA.
3 MA. And I wanted to point out, you would have got the answer right, but I'm trying to help you in case there was a problem where A wasn't 0. You would have just screwed up. You know what I'm saying?
Yeah.
Yeah. So watch out. That's the most common thing people leave out, or they'll screw up one of the minus signs or something. Another common thing is you accidentally switch sine and cosine because you get the angle wrong. So again, this was good. And then the smart thing to do here was that Gage? I think so. I don't know. If so, he's
Angel.
Oh, Angel, my bad. Sorry. Angel, nice job. He said basically set it equal to 0. That's the smart play here. Nice job. Sorry about that, Angel. All right. Let's do this one now. Go ahead and just keep doing the X all the way across. What do we get for this one? Somebody else.
T minus mg equals 0.
Technically, that would be correct, but I think that's a bad habit. Now watch why. Which one of these should be a positive force in this case? According to this
mg.
coordinate. Yeah, so strictly speaking, mg minus t equals 0 for this case.
Okay.
You see where I'm going with that? Now, if A is equal to 0, hey, it all works out and you don't have to worry too much. But again, if A was not equal to 0, you probably just would have lost a bunch of points. So because there's no way you'll get the answer right. If basically, here's the deal. If you just have two things in an equation and you make them and you flip the signs, who cares? But if you have three things in an equation and you flip one of the signs, you're going to run into trouble. And that's what usually happens to students if they aren't paying close attention to the X. All right, so that was that. How about over here? Let's do the Y-axis just to be thorough.
N minus 3 mg cosine theta.
Absolutely. Equals
0.
0. And remember this on the final exam or whatever. If I ask you to write an equation and you don't bother to write equals something, you're going to lose some points. So remember, an equation is always the thing equals something. Equations have to have equals something. All right. Otherwise, you have what's called an expression. So this side by itself is an expression. So, all right, that was perfect. Was that Angel again? If so, good job. All right.
Christian, I believe.
Oh, shit. You can tell I can't see who's talking when I'm trying to. Yeah. All right. So Christian, nice job. All right. Thank you. I'm glad you guys know what's going on. All right. At this point, what are we trying to figure out? Does anybody remember?
We're trying to figure out theta.
Theta. Okay. So again, here's another strategy. What I usually do is force equation or free body diagrams, force equations, then reread the problem, find out what we're trying to solve for. Because by this point, I've forgotten, as you might have as well. So we look for theta. What's a good strategy here? How would you try to do it?
Well, on FBD for M, we could solve for T.
Okay.
And then
what?
use that to plug in T for the FBD 3M for the X equation.
What would drop out after you do that? So do you agree that T would equal mg?
Yeah.
So when I plug that in, look over here. If I plug this in from the other equation, mg, that's coming from right here. Okay, we plug in mg. What does every term have in it that can cancel out?
MG.
Mg cancels out. So this is why I sometimes phrase these problems this way, because it ends up making the math easier if you learn how to do algebra. And so from there, you can get an angle. The rest of the workbook problem works it out. All right, so far so good. A general strategy on this is the following. Use the rotated coordinate system for blocks on a plane. Make sure if you have a string, use that trick where you let your hand kind of guide this thing and use the coordinates that just follow it. Why? If A is not 0, it's tremendously useful. Then use the angle trick to split this thing up and find out where theta is. Be careful not to do the screw up right there. The components must be smaller than the magnitude. Watch out for multiples of m, right? You got to say 3m or 2m or 5m or something. So that appears not only in the mg's, but also in the MAs. What else did we see? And then watch out when your coordinate system gets rotated upside down. Once you write the equation, take a second to double check it before you do the algebra. In general, check your equations carefully before you do the algebra. Otherwise, you may waste a lot of time. If you check them and catch one minus sign, that probably was the only thing you missed. Odds are you're going to either get all the minus signs right or maybe miss one of them. So just double check it, then cruise on through the algebra. Any questions before we move on? I thought that was pretty good performance. Hopefully you felt like you're getting this a little bit. Okay, you could ask Jay anything you want at any time here. I want to look at this one now. 432. It's on the next page. So what is that, 93 or something? There we go. And so I just want to point this one out. 4 blocks, you got 3 strings. Unless otherwise specified, we're going to assume these are ideal strings, massless and inextensible. Zombie pulls the rightmost block, some angle shown in the figure, phi. Friction is negligible, and we are going to assume the rightmost mass actually travels to the right. And then we're supposed to get some acceleration in terms of all these forces and angles and crap like that. Okay, so, and notice in this case, each mass is not necessarily the same. In part B, it says the masses are identical, but for part A, we are not supposed to assume the masses are identical. So the logical thing to do would be called mass 1, mass 2, mass 3, mass 4. All right, so somebody out there, give me a good choice of coordinate system for one of the blocks. Or let me ask, what coordinate system do you think I would start with?
Positive vertical y and positive oh sorry. Yeah, positive vertical y or y going upwards and then x to the right positive.
For which block?
For 2.
Okay, that looks like a good one. I was actually thinking of block 4, but do you agree block 2 and 4 are basically the same?
Yeah.
So it seems to me like this is the logical choice for this thing. Why? Because we're told this thing might accelerate to the right. I don't know if the acceleration is 0 or not, but in fact, it says we're supposed to figure that out, and we know it's going to the right and there's no friction, so it must be accelerating that way here. So notice those two coordinate systems are the same. So what would you do for the other ones? Like, how about block 3? Which way do you think would be the wise choice to put the x-axis now that we have those two coordinates drawn?
You would just shift all the you would just shift all the axes about 45 degrees, right?
Okay, just tell me, is it up the plane or down the plane?
So x is down the plane and y is
Yeah.
up the plane.
Perpendicular to the plane. Yeah. So okay. So again, here the way I would phrase that is I would say x points down the plane and y is perpendicular to the plane. So how about block 1? What direction is x if I follow this coordinate system around just to be consistent?
X is going upwards.
Yeah. And
And
which
then
way is y?
Left.
Yes. Now, you don't have to do this, but this is actually exactly how I wrote the solution. So it helps to kind of do it this way. And notice the idea here is, in this case, you get this pattern where any forces in the y should equal 0. Why? Because none of the blocks are going to accelerate in the y direction. If you look carefully at all the coordinate systems drawn, all the y force equations should equal 0, and all the x force equations should equal m subscript 1, 2, 3, or 4 times a with a positive sign. So I'm going to take a second here. This is the one I thought we might go to the breakout rooms. So I'm going to give you a second in the breakout rooms, and we'll just try this out. So let me split us into 2 rooms. All right. So take a second and go into those breakout rooms so you can actually talk with your fellow students instead of just me harassing you all the time. And yeah, Jay, go ahead and just join whatever group I sent you in there, and you can go in and out as much as you want. All right. Okay, give it a shot. You doing all right, Daniel? Can you hear me, Daniel? All right. We'll give the other group a second to get back in here and just double check here. You could read through some of the other parts and see if you have any questions on that.
So for my acceleration, I got something different than what you put in the book, but that's because I divided it. I left A alone.
What do you mean?
Well, because I divided M1,
Would it help if I
M2,
showed the
M3.
solution?
Yeah, so on the right side, I divided it by M1, M2, M3, M4.
Oh, right. Yeah. Do you agree? Yeah, absolutely. I guess I got lazy. I should actually do that extra step. So A is equal to a bunch of crap divided by M total, right?
Okay, but that's fine then, right?
Yeah. Well,
Okay.
what I wrote technically is wrong because I didn't solve for A. I didn't finish the job. Do you agree?
Well, I mean, you just didn't simplify it. I wouldn't say it's not wrong.
Yeah. Well, let me put it this way. If you had done that on a test, I would have marked off a point because you didn't do the last step of algebra. So
Okay.
I should do the last step of algebra too.
Okay.
It's pretty obvious how to do that last step, but strictly speaking, I should have done it.
Mhm.
So you're right that I was wrong there.
Well, it's
All right.
just because I started looking at the solution for the next one, so I just want to make sure.
Yeah.
Yeah.
So I spent all this time on the FBDs and force equations and forgot to do this. Actually is pretty representative of what I feel is important in the problem. Once you get to this point, that last step of dividing by that is so negligible that's not really worth that much. So you might only lose a half a point out of 11 or maybe 1 point out of 11 for forgetting to do that last step. So usually you'd get lots of points for the FBDs and the force equations and then very small amount of points for the algebra. So everybody, we were just looking at some stuff here. There's a couple things I forgot. In part B, M1 should equal M3 should equal M, and I need to fix that up. And the other thing we were mentioning was that, I forgot to say A is equal to some crap here over M total. I didn't actually solve for A yet. So I should have done that. But just to make sure everybody's on the same page here, notice a couple of things that I did here, and I was talking about this with the other group. For example, in my Y force equations, I just said the up force, the ups equal the downs. Now, you could have said, you could have just as easily said N2 minus M2G equals 0, and that would be full credit as well. In fact, you could even say this. This would be full credit if you'd said M2AY. And then later on, you could change this to 0. So any of those would be correct ways to do it. You could say N2 minus M2G equals 0. You could say ups equals downs. You could say N2 minus M2G equals M2AY, which happens to be 0. All of those would be fully acceptable versions of the force equations in the Y. Excuse me. And then just to be clear, notice this cool trick. If you do the idea of rotating the coordinate system with the blocks and just follow the string, this is the advantage. If you do that procedure where you follow the string with the coordinates, you always get internal forces dropping out on the left and on the that should be right side, shouldn't it? Geez, I totally screwed this up. But on the right side, we get total mass times acceleration. Oh, whatever. Yeah, the math is right, but the words are all goofy. So I need to fix that up. On the right side, we get total mass times acceleration right here. And the idea here is this. If you do the problems the same way every time, you will start to recognize your own mistakes more easily. It's not that this is the right way. It's just a way that we can do these problems systematically. And as an engineer, this is a fundamental thing you should learn. Try to do all the problems of a certain type the same way. Why? You start to recognize your own mistakes and behaviors and patterns. And as a result, you make fewer mistakes and get done faster. That's it. Jay, anything you would say about that?
It seems pretty straightforward. And for me, it's just making sure that the masses are all the same. Like making sure you're keeping track of which case you're using so you use the right masses when you are using that continuous coordinate system.
Got it. Okay. Anybody else? Do you have any questions?
So only when you use that same coordinate system and you twist it, Can you add them together?
You can add them together anytime you want. The trick is when you use this thing where you use this coordinate system following the string, when you do that, we know that adding them all together gives total mass times acceleration on the right, internal forces dropping out on the left. So but you can add the equations anytime you want. It's just sometimes it won't be useful. So adding the equations will work as long as all of the coordinate systems are lined up so that acceleration is with the x direction. That's when it's useful to add them all up. And that's when it gives you this cool trick. Does that make sense? You can add them anytime. Just this is the only time it's particularly useful, in my opinion.
Yeah, it makes sense. Thank you.
Yeah. But you could always add two equations together mathematically, and that's still legal. All right. Good questions. Others?
So what would be the alternative for like drawing coordinate systems? How we did?
It turns out you could do this in an infinite number of ways, pretty much. So there's an infinite number of alternatives, but you could have just always said this is X and this is Y. You could always say this is X and this is Y. You could have said this is X and this is Y. And then you could have, that's one way to do it. Just make all of them the standard XY. It just turns out if you do that, it works great for this one, and this one, but it doesn't work so great for this one because you'd have to split up 3 vectors instead of 1. Actually 4. You'd have to split up 1, 2, 3, 4. So on the angled block, we could see what a terrible choice this coordinate system is. So you could do it that way. You could do all of them having X to the left. You could do any random combination where some of them are up, down, left. X could point any which way you want on any given block. The answers should be the same. The only difference is the amount of algebra you have to do to get to the answers. Does that make sense? Was that Dom? Did I answer your question?
Yeah, I'm sorry.
Oh.
I was trying to unmute myself, but it was being weird. Yes, that makes sense.
Okay, gotcha. Yeah. Other questions? There's a bunch of words here, some other stuff. That's great. All right. Let's maybe take a look at one more here. Let me go to, whoops, get rid of that. Let's go to here. I'll mention, let me see, what do I want to say about that one? Whoops. On this one, here's another one if you want to practice those angles. So notice case 1 and case 2, there's going to be different forces with different angles. So if you were looking for a problem to practice your angles and FBDs and which one's theta, this is a good one to practice, 5.34. Does everybody have that? So 5.34 is a good one to practice your angles. I'll let you try that one at home since it's basically just read the solution and check your own work. 5.35 is a good one that kind of forces, this would be a good review problem for the final exam. I think you'd be crazy not to do this problem as practice for the final exam. So maybe mark that somehow, make a note to yourself. And then let's maybe take a look at 538. So I'm going to give you a second to read this. I'll put the clock up. I'll give you till 12:02 to read this and kind of just get a feeling for it. And then I'm going to ask you some questions in 1 minute. Okay, so that was 1 minute. Oh, let's check the chat here. Gotcha. Okay, so in this problem, I want you to think, how would you attack this problem? In particular, it's pretty obvious that we've got some force problems. How can I tell it's a force problem? Well, it's talking about tension magnitude. That's a force. So whenever we know this is a force problem, and whenever we have force problems, what do we do every single time? First thing, somebody tell me.
Free body diagram.
We're going to draw FBDs. Now, can you tell how many things are going to be unknown in this problem?
Many.
Nope.
None.
2. Parts A and B.
Oh,
Yeah. Let me ask you something. When you do free body diagram, usually how many equations do you get per block at most?
2.
2. And that's a sign that there's usually 2 things that could be unknown. So all these problems, it's basically use physics to set up algebra equations so that you get 2 equations, 2 unknowns, and go to work. Now, there are some, you could argue maybe on the last problem, you could say that's 2 unknowns per block because there could be unknown tensions. Now, some of them like this one, that's only going to give you 1 force equation. So that could only have 1 unknown. But we might expect maybe 2 unknowns per block. All right. That said, we know we have to do FBDs. Which FBDs would you draw for this system? We got 3 blocks. How many FBDs do you think we might need?
Two.
3. So usually you need 1 FBD per block. So, right, if there's 2 things that could be unknown per block, we might expect you might need an FBD per block to get the equations needed to solve for the unknowns. All right. Maybe I don't know if I'm confusing you, whatever. Just remember this. If you have 3 blocks, this you can remember. If you have 3 blocks, you need 3 FBDs. All right. That if you had 7 blocks, you'd need 7 FBDs. Look at the last problem. We had 4 blocks. We needed 4 FBDs. So in general, usually this is the way it works. The number of FBDs, you need 1 for each object. Okay. All right. What would be the good FBDs to draw here? Any ideas? You could obviously do block 1, block 2, and block 3. That would always work. Do you see any other FBDs that would be legal mathematically?
The system?
You could do a system. Where it's going like this. Now that's kind of tricky. So in this case, maybe that would be challenging. So this would be a 1, 2, 3 system. You could do that. Is there another FBD you could draw that's maybe a little bit simpler?
System 2-3.
You could do a 2-3 system, right? And so those are the ones that jump out at me as the things you might do here. So you could actually do an FBD. Now, what is the advantage of the 2-3 system? If you do a 2-3 system FBD, what does that get rid of?
The internal forces.
What is the internal force between 2 and 3?
The normal force between 2 and 3.
So that gets rid of part B. Do you see that? And so by doing this, it turns out you could actually do the system FBD and then maybe block 1, and that might give you the first part. And then you could go back and do block 2 or block 3 to get the part, this section, the second question. Now, which FBD looks easier, block 2 or block 3? Which of those 2 FBDs by itself do you think is going to be easier to deal with?
2.
2. There's just fewer forces on it, right? You don't have the tension from the string. And so we see that I would actually choose, like if I was trying to be as efficient as possible, I would choose this one, and this one. However, if I didn't want to be clever, I'd just do 1, 2, and 3 and get the job done and forget about this system crap. And that will always work. So those are the 2 ways you might approach this one. And that's how the system might be useful on rare occasions. Anyways, I just wanted to allude to that. Any questions about that crap? You can always do one separate FBD for each block, and that'll get the job done. If you were clever, in this case, it turns out the system for the 2-3 block might save you some time, and then you could skip this block 3. Oh, help me out. Answer question part C. While it's accelerating, does block 2, whoops, this which needs to be cut out. Does block 2 exert more normal force on block 3, or is it the other way around? While it's accelerating. What do you think?
They exert the same amount of force?
Nice. I was trying to trick you. It doesn't matter if it's accelerating at all. That was totally a decoy. They're always the same by what law?
Newton's third law.
Nice. Newton's third. All right. Okay. What do you think? Let's maybe end with a simulation here really quick. All right. And so you can see here, let's go ahead and put this thing here. Right now, I don't know if you could tell up here. Notice I've selected the no friction mode right now. And so I'm just going to kind of foreshadow what this looks like and why this gets tricky. So what I'm going to do, what I could do is I could apply a force here of 10 newtons and we see what happens. Let's do 50 newtons. So when I hit enter, right, I'm going to pause this for a second. The idea here is maybe you can see this, maybe you can't, but right here, there's a small arrow to the right that represents 50 newtons, okay? Now, in this case, this is the classic problem where friction is negligible, right? So maybe this zombie has spikes on his shoes, so the zombie can grip, but the box has no friction here, okay? So in this case, let me clear that out. I'm going to keep playing this one. Notice the box keeps moving faster and faster. Let's go back here. Let's try this thing with 100 newtons. And so think to yourself, what should be happening? Should it accelerate at the same rate or faster? Notice it's not just moving to the right, it's accelerating to the right. You could tell, let's jack this up even more. Oops. Okay, and then if I hit play, we get this large acceleration now. Again, it's not moving with constant speed. So if you look at the sum of forces, let me hit pause here. The idea here, this green arrow shows you the sum of the forces, right? The normal force cancels out the force due to gravity. The applied force from the zombie ends up being the net. Now, what happens if we do this on an incline? Whoops. This is where things get a little bit tricky. So when I do this one, let's reset this. Oh my gosh, this is going to be tricky. All right, let's return this object. Okay, so now I'm going to start here. I'm going to do the same thing, and I'm going to push this thing up the ramp with 50 newtons. Oh, let's go 100. Now, in this case, where it gets tricky, I find this kind of funny here. Oh, let's make this 175. So the idea here is when it's trying to go up the hill, now let's start right here. All right. In this case, think carefully now. This is the direction it's accelerating at this instant in time, okay? Because there's nothing to oppose this horizontal force. Now watch what happens as this thing goes up the ramp. Watch the gravitational force. In particular, does the gravitational force change? Watch it. Right now, the gravitational force has not changed, but what does change is there's now a component down and a component this way. And notice this component is larger than the force the zombie is applying. So now there's a net force down the ramp. Which way is this thing accelerating right now? To the right, left, up the ramp, down the ramp, perpendicular to the ramp? Which way is this thing accelerating right now?
To the left of the ramp?
Yeah, down the ramp. So even though the zombie is still pushing up the ramp, right now the weight force is too large, and so the zombie is able to slow it down but not stop it. Good. So let's run this. Let's keep running it. So now watch this. At this moment, which way is this thing moving?
Moving to the left.
Yeah, so it's moving this way. So this is the velocity. Which way is it accelerating?
To the right.
And so is this thing going to speed up or slow down?
Slow down.
And so all of this stuff that we've been talking about with the kinematics and the simulation, it all comes together.
So I had a quick question.
Yeah.
I was wondering about the shift in like acceleration, how it starts accelerating to the left.
Mm-hmm.
Does that happen because like normal force changes and like
Yeah, watch the normal force. The normal force actually does change. Do you see it? Is it
Yeah.
am I able to show the values here? I forget if I could show the values.
Because that's what I was thinking, like was the cause of it, but then you said that
Let me make this more dramatic.
well,
There you could really see the normal force changing. The idea here is, let me get it up there. Let me make this 250. Let me do one more. Hold on. Okay, at this moment, right? The idea here is the weight force never changes, but the component does. So what does the ramp do? The normal force up here is opposing this portion of the gravitational force, this portion of the weight force, right? So the idea is the weight force, this main component, the main thing here, or sorry, the magnitude of the weight force does not change. When you put it on a ramp, the component of weight force does change. That changes the normal force. But it, right, because the normal force only has to support the portion perpendicular to the ramp. So this portion parallel to the ramp doesn't care about that. That could just slide back right back down. Is that helping, Dom?
yeah. So yeah, that helps. But I was just wondering, could you say that like the other way around and say that the component of the normal force is changing and that's what's causing the movement?
No. I would say the normal force changes as a consequence of the ramp angle changing. It is not the other way around, right? Because the normal force magnitude is reacting, right, to the box pushing down on it. The box pushing down on it comes from the gravitational force, right? Because the gravitational pulls the block downwards towards the center of the earth, that's what causes the box to push downwards on the ramp with the normal force. As a reaction to that, the normal force pushes up on the block the opposite way. And it's just, that's the right probably way to think about it. You don't want to start with the normal force and say that everything, I don't know. Mathematically, I know they're the same, but it's just, I don't know. I'm a physics teacher, so I can't help it. Does that make sense?
Yeah, that makes sense. I was just looking at it like I just noticed the normal force changing first, and that like that's why I was just kind of curious about that. And then you pointed out the components of the of gravity. So I don't know. I just wanted you to explain that a little more, and you did. So thank you.
Okay, cool. Let's have a little fun with this one. So think about this. Let's say we use this angle right here, 41.8 degrees. How hard am I going to need to push this if you had to guess? Just kind of look at these components and eyeball it, right? So if you see this, how hard do you think I need to push this so that it actually goes up? We know that this orange arrow right now is 250. How hard do I need to push it so that it actually goes up all the way to the top of the ramp? What do you think?
Probably about 750 newtons.
Yeah, probably. So let's give it a shot and let's see what happens. So if I push this with 750 and hit play, let's see what happens. Oh, nice. Let's see what happens. Oh my gosh, we crashed the block. End of the world. Okay, so now we only have 3 minutes left. I want to show you how much nastier this gets if you put friction involved. So let's start with the level incline. Why is friction so tricky, and why are we splitting that out into next week's class? Let's say I start here with 100 newtons of force, and I'm going to apply this and hit play. Whoops. It doesn't go anywhere, right? Friction is sufficient to stop it. What if I do 200 newtons of force? It still doesn't go anywhere. How about 300? Still doesn't go anywhere. How about 400? Not quite enough. 500? Oh, there. We're about there. So let's do 550. In this case, I want to point this out. Now there's actually, oh, did you see that? Oh my gosh. Okay, let's go back here to, how about 480? Oops. Let me reset. Let me just finish this out. All right. So right here at 450 newtons, it's still not slipping. So think about this right now. I just want to point this out. Right at this moment, I'm pushing this way with 450. What is the acceleration right at this moment? This thing is actually running right now. What is the acceleration?
0.
0. So if the acceleration is 0, what is the force of friction right now?
450 newtons.
Exactly. Ooh, I like that. Let's stick those units on there too, just to be thorough. Okay. So at this moment, now watch what I'm going to do. So as long as it's not moving, do you agree that the frictional force and the applied force should balance? Whenever it's not moving, whatever number I have down here should be the same as friction. So I'm going to slowly creep this thing up. Maybe. Oh my gosh. Let's try 480. It's still not moving. Let's try 490. Still not moving. Let's try 500. It starts moving. Now look, I just want to point this out. Look at the size of the arrows. Is friction still equal to 500?
No.
No.
No. This is very tricky. What happens is if the objects aren't moving, friction can balance the applied force. Okay, fine. But once you get it moving, friction suddenly drops dramatically. In short, it's much easier to keep something going once you get it started than it is to get it started moving. And so we see down here, I want to point out, we're going to talk about this next time. There are actually two different coefficients for friction. One of them is for when it's static, and the other is for when it's actually moving or kinetic. So friction will depend on now, okay, so we see that friction depends on whether or not you're moving. You actually get less friction once you're moving. Great. Now watch this. What if I put this thing on a ramp? This gets really complicated. All right, let's just hit play here and watch. Watch what happens to friction. Look at this. It's, oh my gosh, this sums it up. Let me put the block over here. Let's start here. So what I'm going to do is I'm going to push with 500 newtons here. Let's do 550. Oh, 500 is fine. Notice as it goes up the plane, friction stops, and now it reverses direction. Also, notice it got a lot smaller, and it's no longer accelerating. friction is a very tricky force. My goal in showing you this is showing you that we need to talk extensively about friction. We see that friction can change directions on you, even though you're pushing the same way. Your acceleration can change from something to 0 or 0 to something. And when you put this thing on a ramp, it's very complicated. So why don't we leave it at there? And that'll be my foreshadowing. I didn't get to do as much as I'd like, but we'll pick this up next time. And it suffices to say friction is a very complicated force. That's why we're basically doing only friction problems in chapter 6. We'll address all of those different situations where you could be moving to the right and slowing down, or on a ramp and then it's at rest, or it's not accelerating, or it's accelerating the wrong way. Yeah. Sometimes friction can point the direction you're accelerating. Sometimes friction points opposite the direction you're accelerating, but it tends to point opposite relative motion. It's going to be crazy. Yeah. So the next chapter, chapter 6, is all FBDs and dealing with friction.